Up until this point, we have looked at several kinds of geometric objects, like scalars, vectors, bivectors, and so on. With the exception of multiplying any of these objects by a scalar, we have been considering them to be completely independent from each other. What operations can we do that involve a mixture of grades? That is what we will look at in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. There are two important operations that we can do with these objects: addition and multiplication. Sadly, we are still not quite at the point that we can talk about multiplication yet. Don't worry, you only have to wait for a couple more videos for that one. In this video, I want to focus on addition. So how could we add objects of different grades? Well, think back to how we defined addition for scalars and vectors. We simply said we can add them without having any geometric picture and manipulate the sums purely algebraically. Formally, we do this with the direct sum, which takes two linear spaces and produces a new linear space that contains both of them. If you're not familiar with direct sums, you might want to check out my previous video on the topic. We can use a direct sum to add all grades together as well. We can take the direct sum of all grades to produce one single linear space that contains them all. Because this space contains multiple kinds of k-vectors, we call them multivectors. Now you might recall that in my original video on direct sums, I said that the sum of a scalar and a vector is not all that useful. It's a completely different story for multivectors. Multivectors are the fundamental objects in geometric algebra. One thing I want to point out is that while I am writing this direct sum in a way that seems infinite, given that we can't have things like trivectors in 2D, these direct sums are always finite, at least when working in finite dimensions. For example, a 2D multivector is just the sum of a scalar, vector, and bivector, and a 3D multivector is the sum of a scalar, vector, bivector, and trivector. Describing multivectors abstractly like this might seem complicated, but when you actually work with them, you'll see that they're not that bad. Let's take a look at 2D multivectors. In 2 dimensions, the only objects we have are scalars, vectors, and bivectors, so a 2D multivector is just the sum of a scalar, vector, and bivector. We can get even more concrete about this by considering this in terms of components. A scalar is given by one single component, a vector is given by two components, and a bivector is also given by one component. So all 2D multivectors have this form. Looking at it, we see that 2D multivectors have 4 components, so they are algebraically 4-dimensional. Multiplying the scalar component by 1, we see that the standard basis for 2D multivectors is given by 1, E1, E2, and E12. Using this basis, we can do calculations with multivectors in the same way that we do calculations in other linear spaces by adding and scaling the components. And that's pretty much it! For 3D multivectors, we have scalars, vectors, and bivectors again, but we now also have trivectors. Looking at components, we have one scalar component, 3 vector components, 3 bivector components, and 1 trivector component. Notice that even though the only new kind of object in 3D is trivectors, the other grades got more components from the jump to 3D as well. In 3D, multivectors have 8 components, so they are algebraically 8-dimensional. We see that the standard basis for 3D multivectors is given by 1, E1, E2, E3, E12, E13, E23, and E123. Once again, we can use this basis to do calculations with multivectors in the same way as before. One thing you may notice is that the algebraic dimension doubled when jumping up a dimension. In 2 dimensions, the algebraic dimension of multivectors is 4, while in 3 dimensions, the algebraic dimension is 8. Looking at 1 dimension, we only have scalars and one single vector component, so in 1 dimension the algebraic dimension is 2. So it seems that the algebraic dimension of multivectors doubles for each increase in the geometric dimension. Is this true? More formally, is the algebraic dimension of multivectors in n-dimensional space 2 to the n? Well, remember from the last video that the algebraic dimension of k-vectors in n-dimensional space is n choose k. It's a standard fact about binomial coefficients that the sum of n choose k for all k from 0 to n is equal to 2 to the n, which directly proves our conjecture. And if you would rather not appeal to random facts about binomial coefficients, it's possible to prove this directly too. Notice that when jumping up a dimension, all of the previous basis multivectors still exist in the higher dimension, and all of the new basis multivectors are all of the old ones with the new basis vector added on. This doubles the algebraic dimension. Now, there's one fact about direct sums that I want to bring up. When doing a direct sum, we think of the direct sum as containing the original spaces. This means that every element of the original spaces can also be thought of as being in the direct sum. For multivectors, this means that all scalars are multivectors, all vectors are multivectors, and so on. This can be seen a little more concretely by looking at an arbitrary 2D vector. Because adding 0 doesn't change anything, this is equal to a 2D multivector with the scalar and bivector components being equal to 0. Now, it can be useful to differentiate between the multivectors that are built from a pure k-vector and the multivectors that are built from a mix of grades. We say that any multivector that is built from a single k-vector is homogeneous, and all other multivectors are not homogeneous. For example, 4, 3e1 plus 2e2, and negative 3e12 are all homogeneous, but multivectors like 2 plus e1 and e2 minus 3e12 are not. Like we saw in the video on direct sums, we can show that all types of 0 are equal in the context of multivectors. The scalar 0 is equal to the multivector 0, the vector 0 is equal to the multivector 0, and the bivector 0 is equal to the multivector 0, so they are all equal to each other as well. When being really rigorous, you do have to make some distinctions, but in almost every other case, it doesn't hurt to consider the zeros to be equal, and doing so makes things much simpler. Now, it's common in math to give important sets a special symbol, such as blackboard bold letters for the various basic number systems. Should we do the same thing here for multivectors? While it's not too common, I personally like to use a blackboard bold G to represent multivectors because this is geometric algebra. However, one issue we run into here is that we have multiple types of multivectors. We have a different set of multivectors for each dimension. Thus, we need to put the dimension somewhere in the notation. I've seen people put the dimension in many different places, and there doesn't seem to be any fully universal standard at the moment. Also, while I personally won't use it, instead of using the blackboard bold G, people often use CL, which is short for Clifford, the father of geometric algebra. Other than the letters used, the rest of the notation is the same. Also, this notation will morph a bit as we get to more advanced topics, but for now using one of these is good enough. The last thing I want to talk about in this video is what is called the grading of multivectors. I already introduced the term grade in the last video, but it's a little more general than I made it seem. In general in linear algebra, a graded space is a linear space that can be written as the direct sum of other linear spaces, usually with the other linear spaces being indexed by the natural numbers. This is precisely how we defined multivectors. They are the direct sum of all k-vectors, where k is a natural number. Thus, in this sense, multivectors are a graded space. We then call the kth space in the direct sum the grade k subspace of the graded space. After adding several grades together, it can often be useful to undo the sum. For example, if we have a multivector that was created by adding a scalar, a vector, and a bivector, we might want to get the scalar, vector, and bivector back. We can generalize this idea to extracting any particular grade from a multivector. The notation we use for this is these angle brackets around the multivector we are working with a subscript saying which grade we want to get. Using this notation, here is our original example of getting the scalar, vector, and bivector parts from a multivector. Also, when taking the grade 0 or scalar part, we often drop the 0. So if you see plain angle brackets around a multivector, it means to take the scalar part of that multivector. To help you get a handle on the grade projection operator, let's do an exercise. Please calculate the following grade projections. Hopefully, this exercise wasn't too difficult. The first 4 grade projections are pretty simple, so I won't talk through the process and just show the answers. The 5th one is a little stranger since it's asking for the vector part from a multivector that has no vector part. However, we could instead just think of the vector part as being 0, so the grade 1 projection in problem 5 ends up being 0. The 6th problem is a little silly in that the multivector is already a grade 2 multivector, so the grade projection ends up doing nothing. The 7th problem is similar to the first few, And the 8th problem was just checking to see if you remembered that angle brackets with no subscript means to take the scalar part. Up until now, we have mainly been focusing on various linear spaces, like vectors, bivectors, and then multivectors, which contains all of those. However, linear spaces only have addition and scalar multiplication. While addition and scalar multiplication are pretty useful, there has been one glaring omission: general multiplication. The way we multiply is what sets geometric algebra apart from other branches of math. The next chapter will be entirely about the way we multiply multivectors and some of the consequences of this definition of multiplication.